Okay. Sharon, Brian, can you hear me?
Go ahead, Tim.
Okay, great. Hey, everybody, thanks for joining in today. This is Tim Farmer. I'm the manager for Service Engineering's Aberdeen Research Operation, and I'm glad on behalf of DSIAC that they would sponsor this webinar. We're going to hear a little bit later from Alex Bernardo. Just by way of a quick introduction to our company, many of you I recognize here on the attendee list, so many of you are aware. Service Engineering is a small business, nearly 40 years in business, focused on survivability and lethality of land, sea, and air systems. So there are a bunch of different core competencies: technology research and development, so conducting research, development, prototyping for next-gen technologies in the way of reducing vulnerability, enhancing survivability and lethality. Studies and analysis, test and evaluation, models and tool development, information technologies, and then metrology and reverse engineering. And can bring any of those capabilities to bear to support folks in the community. If you've got any questions, you can always find more info at www.survice.com. And for those that may not know Alex Bernardo is a senior engineer at Service Engineering. He has physically been on site supporting our Washington area office, our Michigan area office, now here at our Aberdeen area operation. He's got more than 20 years in research, development, test, and engineering, predominantly in the military vulnerability field. His past work has included planning, conducting, reporting of ballistics and explosive testing. He's also performed pre- and post-test analysis using a variety of mathematical and numerical models, ranging from first principle to empirically based. Mr. Bernardo holds a BS in aerospace engineering from University of Washington and a Master's of Science in Mechanical Engineering from California State University, Northridge. So with that, Alex, looking forward to your presentation.
All right, Tim, thanks so much for that intro. And thanks everybody for attending this webinar.
Hey, Alex.
First, I would like to... Hello?
One other point. If you guys have questions, I should have said this before I introduced you. Sorry, Alex. If in the center of your, the upper middle of your webinar, you will see that comment box, 3 dots and 3 lines. It says View Audience Questions. If you click that, if you'd like to add your questions all along the way, we should see them there. If you happen to use the attendee chat function, we'll try to port those over to this question list so that Alex at the end of this can respond. Thanks.
Okay, so again, thanks everybody for attending this webinar. Much appreciated. Thanks, Tim, for the introduction. The title of the talk is Applying SC3D to Verify Force Protection with Hard Kill Active Protection Systems. I would like to recognize my co-author, Pat Buckley, who is also with Service Engineering. He's the author of the code SC3D, and none of this would be possible without him, obviously. So just a little bit of a background. Service was asked by the Marine Corps to find a best option for them for their amphibious combat vehicle and a best option active protection system for them for their vehicle. And we looked at various systems of technology readiness level of greater than or equal to 8. And in doing so, we had to identify certain selection criteria with these different options, including performance and SWaP-C being space, weight, power, and cost metrics that are associated with each of these systems. But in particular, the performance portion of it was tough to get our arms around. And so we had to come up with some sort of quantification methodology. It's easy to quantify the SWaP metrics, but it was harder to quantify the performance metrics. And so we used SC3D as a tool, and it allowed us to do some more qualitative estimates, or quantitative, in fact, estimates of the survivability that's associated with countermeasure engagement with hard kill active protection systems. But in particular, though, with this phenomenon called early initiated normal jet. And this added parameter of having to understand survivability associated with composite armor was also important. So this approach, this methodology allowed us to kind of get a better handle on the survivability performance aspect of active protection systems. One thing to note, though, that there are other outcomes that are possible when a countermeasure engages a shape charge or a threat that's incoming, apart from early initiated jet. And I wanted to cover that a little bit as well for everyone's understanding. And this table here is from the Army SLAD folks out at Aberdeen. And they're working also on trying to get this quantified, to have a better understanding of it. And straight from the top, you have kind of the more deadlier encounters with the threat, or deadlier engagements with a threat, starting off with a built-in standoff when the normal jet is initiated, and then we have an early initiation with normal jet, or the AINJ outcome that we're specifically looking at. You can also have a built-in standoff, but with a damaged jet, and you also have down the road reading through early initiation if a jet is damaged with a countermeasure, and if some standoff, say the countermeasure engages the threat and the detonation is produced, you also have that particular outcome. And that's all when a jet is produced, or when some sort of very energetic outcome is produced that can cause damage to your target, or to the target of interest. So that's kind of the top part of the table. Now, then you also have the bottom part of the table where there's non-jet producing outcomes that occur, going from fragment-induced reaction, dud, dismembered warhead to crush up. So things that'll still cause you some problems, but not nearly as bad as the jet producing outcomes. And one thing that I wanted to point out is because active protection systems have been, there are active protection systems out there, obviously, and then we worked as best as we could with the information at hand, with whatever we can get at, to try to understand what the probabilities of these different jet producing outcomes are and non-jet producing outcomes are. And then that's one of the toughest things to try to get at this point, because there's not a whole lot of data to try to get that information at this point. But in doing our quantified approach, we decided, along with our customers, that, well, if we at least look at the early initiated normal jet probabilities, or just assume that happened, that's kind of one of the worst case scenarios, apart from a built-in standoff normal jet. And so we managed to kind of narrow down the area we're looking at, with the understanding that the other jet producing outcomes are not as bad if they do occur. And so that's the rationale for going deeper into the EINJ phenomenon and doing the analysis from that context. So more background. SC3D. It's Service Crone, again written by Pat Buckley, and it was originally written as a design tool for shape charges, and where you could do shape charge analysis versus RHA or steel armor, and input in the geometry of a shape charge to your heart's desire, to try and understand, or to try to be more effective, to try to determine if you can have an effective shape charge. And then you can test it against armor and see if you have improvements in penetration. And it was predominantly done for single shot target, and you can also do it again for single shot target analysis, where you can load a 3D target and you can try out that shape charge against some sort of armored target or not armored target to determine if you have what the effects are of, say, increasing your armor against this shape charge, and to determine the trade-off or the play between an armored target versus a shape charge that you're either designing, or a shape charge that's already a known quantity. And so either or, it can be kind of used as either a lethality in a lethality approach or a survivability approach. Right now, it's being extensively used by naval surface warfare for ship survivability, and Pat Buckley's helping them out on that. And more importantly, though, we're looking at the jet breakup. We also have in that code jet breakup associated with incoherent shape charge at standoff. And so that's kind of the critical to understanding what happens when we're trying to understand what happens to survivability as we evaluate the countermeasure or EINJ that's associated with countermeasure engagement of the shape charge. So in terms of what we've been doing with Service, we had an internal research and development funds that added additional utilities to SC3D to look at this residual damage from shape charge, early initiated normal jet. In particular, we're able to try to get now penetration through composite armor. And with that, what I was going to talk about with you was to do an exercise in getting the RHA equivalent for some sort of composite armor. And once you have the RHA equivalent for composite armor, then you should be able to use that to do traditional vulnerability assessments for tools like Moves AGEM. And we have our own tool just like that called Turbo PK. And because right now those tools don't necessarily have that capability, but they're working towards them. And so this gets you kind of a quick way to get through it. We also have a capability in SC3D where we can get a probability kill given a countermeasure intercept of a shape charge. And this is with a single burst, called a single burst point. There's certain, it's actually really an EINJ event that is that we run stochastically, and it's not like a single point thing. It's a Monte Carlo run, so we can get a probability of kill with that particular intercept. And we also have this new capability of getting a PK given a launch of. So we have a hard kill APS countermeasure intercept, and we suppose that this intercept occurs on a geometric dome. And so given a launch of a threat and given a name point and giving an as-an-L attack vector, then we suppose that the intercept occurs at this dome. And this analysis involves circular error probability and using Monte Carlo. And I'll get into each one of these approaches in more detail. So going into the first kind of analysis that we can do, and this is an example of getting an RHA equivalence of composite armor. And this is a sample exercise. So this is harkening back to SC3D's capability to come up or look at shape charge designs where you can input in whatever shape charge parameter, geometry, physical properties where things occur within the shape charge, and then determine what happens to the penetration depth into a semi-infinite RHA or RHA slab versus standoff. So this portion of it at least gives you kind of your sanity check where you are indeed modeling the shape charge correctly, if you are modeling indeed some sort of real shape charge, and gives you a reality check of what you're seeing. So this is kind of the original part of it. But in this analysis, we input, I've input in a hypothetical shape charge of kind of the variety that we normally encounter out there in engagements. And this is where we start off with in this analysis of getting the RHA equivalence against composite armor. So as we move along, so once the shape charge is input in, then we can um, look at some sort of armor recipe. And in this particular case, it's just a hypothetical armor recipe with ceramic, aluminum, RHA, and fabric in there. And then it's just kind of layered in some random fashion and some random thickness. And just to take a look at it. Not optimized for anything. This is just a sample. But what we're really interested in is getting where the probability of penetration goes to 0 versus standoff. So we want to understand at what standoff the probability of penetration drops to nothing, and use that information. But in this analysis, we we look. So the first thing we need to understand is if it's a composite armor that's newfangled and we don't know anything about it, we need to input in what's the closest standoff and what's the farthest standoff that we do our analysis in. So that's input into this run, and we can also put in the number of times for each standoff, how many times in a Monte Carlo fashion is evaluated. So each of the dots that we see in this chart is actually 100 Monte Carlo runs. So it averages out over 100 runs what the probability of penetration is. And within the code, though, the penetration is measured by the simulation actually has a semi-infinite slab of RHA on the other side of this armor recipe. And so if that RHA slab sees any part of the jet impacting it, then over these number of runs, then the probability of penetration is recorded thusly. So this is how the chart is created. But in this particular example, we've got this composite armor, and we've characterized the composite armor over a standoff range, and we have this now understanding that about 200, 220, 230 centimeter standoff, we're at near 0 probability of penetration. So we take that bit of information from this analysis, and then what we'll do is we'll go run let me step back just a little bit as an illustration and as an added feature of this analysis. It does in real time at each standoff provide you with a graphics of what the jet particle spread is and the penetration is for that particular standoff. So in the upper left, we have a jet particle spread at 50 centimeter standoff, and then we do that. What we do see is that the spread is not very far; it's very narrow, which is understandable. It's a good a nice sanity check of what's supposed to happen at 50 centimeters. And on the upper right, we have an upper. In the upper right, we have the penetration into that RHA slab behind that armor recipe, and so that's quantified. And so each time we run this case, it's verified that the probability of penetration is high, if not all the time. But then as we step out in the lower left, we've got the jet particle spread at 230 centimeters standoff, and then that visually gives us a sanity check that the jet particle does spread apart. And then on the lower right, we have a visual penetration of what's happening in one particular case at 230 cm standoff, and we see that there's no penetration in that case. So this is happening when we make that run that goes from 50 cm to about 300 cm. in evaluating probabilities of penetration through that armor recipe. So, but now again, we have that nugget of information from this analysis of about 230 cm standoff. And so we take that piece, and then what we want to do is run it with just run the same analysis with just pure RHA, because what we're trying to do is find out the RHA, the equivalent RHA thickness that produces the same performance as that armor recipe. And so, in this particular slide, though, I've got it at about 2 cm for RHA. And then, so what happened was I got lucky. I ran it between 50 cm standoff to 300 cm standoff, and then it just so happens it's more or less fell at about the same performance as that armor recipe that I just made the run for. But if I had guessed wrong, say if I had guessed, well, it's the same RHA equivalence as 3 cm, then I would have seen the probability of penetration to be lower, so that we would have had that standoff would have been greater when that lower, when we would hit that zero probability of penetration. And if I had tried it for 1 cm, then the probability of penetration would have gone down to zero at a shorter standoff, obviously. So it's not being shown here, but in this particular case, I just kind of haphazardly got lucky with this 2 cm illustration. So the bottom line is, though, that hypothetical armor recipe that we did the analysis in, we just had is equivalent to about 2 cm of RHA armor. And then that's the information that we use in the traditional vulnerability assessments in trying to understand what and then at that point we use that information to understand the survivability of the vehicle and the target vehicle and the components within. So they're getting the RHA equivalency done. Now let's move on to occupant vulnerability with a single countermeasure intercept. In this example, I use a sample target geometry. It's the BMP2, and in this particular scenario, where I've got the occupant set as the vulnerable components, and just to make things kind of simpler, I don't have any fault trees in there, and I've set each of these components to be a kill at an impact, a jet impact of 0.1 centimeters per microsecond. And so that's our kind of fall off on when that component is killed. And this exact example here is just a single EINJ event of an 80 millimeter diameter threat. And we pretend that the intercept occurs at 5 meters from the vehicle. That's all input into the analysis. And jet model breakup that's associated with incoherent shape charge is modeled as well. And so and then the Monte Carlo one is set to 50. So in this particular case, because I'm aiming for a particular vulnerable component, we get a kill with this ASL and aim point for that particular component. But at the same time, just kind of visually, we have this understanding from a visual standpoint that you would have to be aiming for these. And so what would happen in sort of like a vulnerable area type of analysis is really its projected area for this standoff is what occurs as being vulnerable for these vulnerable components. So we have that kind of understanding. But at the same time, though, since I'm aiming at the top of the vehicle where the armoring is low, then we do get a component kill. If I had aimed for, say, at an AS&L that is going through some armoring, then our probability of kill would be, or probability of kill for that component would probably not be at all or as high. So that's kind of a one-shot analysis of understanding occupant vulnerability with a single countermeasure intercept. Now I'll move on to understanding probability of kill given a launch. And within the code itself, we use what's called a circle error probable. And we apply that to a dome, some sort of protection dome that is about the target. And this is where we assume that if there is a launch or if there's um, an intersection or an intersection of a threat coming through this dome, that's the dome is where the countermeasure would would set off the shape charge and initiate it as an early initiated normal jet. So given this launch, so that circle of error probability is essentially overlaid on this dome, and that CEP or circle of error probability is governed by this formula, and it's a kind of a classic Rayleigh distribution, and the analyst has an opportunity to kind of dictate what that CEP is in terms of just inputting in a radius, but the guts of it is it uses this formulation to get in there. And for each one of those intercepts, each one of those, a Monte Carlo is run. And so that gives us a better kind of statistical idea of what might happen if a threat is launched at a vehicle that's that's aiming at a certain aim point, and if we take into account things like the probability that that launcher in, may not be as accurate in aiming, and there's going to be a big difference in how that launcher is aiming and where that threat is actually going to be intercepted in this protection zone. So we're taking all of that stuff into account and then trying to assess what the vulnerability is of that event. And so in the slide that I'll be showing, we're using the same target, that BMP2, same threat, the 80 millimeter threat, and I've selected an aim point and an attack as as an engagement parameter. And so here we have kind of that one scenario where I've inputted at the top, kind of top middle, the ASL and the aim point, and more importantly though the CEP, the circle of error probable, and then that's where, as an analyst, we kind of have an understanding of, okay, well, if it's a shoulder launched, then they're not typically very accurate at aiming and shooting, because sometimes they're getting shot at. But if you're talking about an ATGM and you have kind of a target reticle and you may be at a higher standoff, you have a better shot at making that CEP smaller, then you would, as an analyst, would kind of take all of that stuff into account. And within this analysis, there's the number of trajectories. How many trajectories within the CEP am I going to try out? And I've set it at 50, but we've only come up with a handful of actual intercepted trajectories that's associated with that CEP. So a big chunk, because the CEP is kind of large, then our actual intercepted trajectory becomes small. Now I can play around with that and make it smaller, and then really have a concentration um, interceptions of the countermeasure with the threat, and so that we can evaluate that. But that really depends on where you think that CEP is going to be based on the threat that you're encountering. And for each one of those intercepts, though, I've got it set at 20 Monte Carlo runs, and so with this CEP calculation, and then with the Monte Carlo run, and then we're doing the same thing that we did. Each one of these shots at 20 times, each time it evaluates an incoherent shape charge at an EINJ as an EINJ event, and we're trying to evaluate, well, is it going to hit any of our vulnerable components within this target? And in this particular case, we were at 0 because of the large CEP, and then and because it just ends up being the components, at least of the vehicle that we're interested in, which is the occupants, don't occupy a lot of the projected area across this dome. So we're coming up with PK of 0. So obviously, you can play with this thing, and if you've got a smaller CP, like I said before, you should come up with a non-zero PK. Okay, so that's for this third example of what we can do, or what we've done with SC3D, and just heading off to concluding this talk. So we were able to get an RHA equivalent for armor recipes that include fabric and ceramics. We're able to do an occupant vulnerability analysis with a single burst or a single EI&J event to understand what happens for a single engagement event. And we were also able to get a probability of kill for a countermeasure engagement given a certain launch, understanding that there's things that need to be taken account when a threat is launched at a vehicle. So either way, we're able to kind of get our hands or arms around kind of getting a much more quantitative understanding of the performance of an active kill protection system, hard kill active protection system. And with that, I guess what I need to do is to flag questions, and I saw that there were a bunch of pop-ups with a bunch of questions. I guess what I can do is go through them, if you'll permit me.
Yeah, Alex, I'm going to show this question to the audience.
Mm-hmm.
So for those of you that can't see it, you may be able to click on that icon in the upper middle, the comment-looking icon, but you should see this now. In the background slide, this question by Eugene Fleeman. You mentioned TRL greater than 8. So he's familiar with the NASA definition of TR, but have not seen a DoD reference for definition of TRL. Could you provide a DoD reference for the definition of this technical readiness level?
They're pretty much the same, is the nutshell answer to this. Because we used it as more of a guide. There's a DoD guide which kind of refers to the NASA, which is in the government, and they're roughly the same. But what exactly happened was, there weren't any technologies that kind of fell right on that TRL 8. You're either pretty good or you're either pretty bad. So we didn't really have a whole lot of opportunity to kind of apply strict definitions to it. And so, so it's like, okay, well, you're good, you're above, you're not even questionable, or you're pretty bad and we're not even going to take you. So we weren't really in a quandary where we had to like nitpick that TRL level between how the DoD and the NASA defined it. So I hope that answers that question.
Okay.
Okay.
Cindy Sharp and a few others have asked if the slides can be made available. Brian, feel free to jump in if you wish, but I provided a link in the chat window, and that link and these slides should be available on Service Engineering's website. If once we get these posted, we can make sure that all attendees get the updated link. Okay, Joel Williamson's question. He's got a few here. Can the code be used today to examine fragment-induced detonation, curved jets, and damaged jets?
Well, that's a very good question. But the straight answer is we're working on these very specific events or outcomes of when a countermeasure more or less severely affects the jet formation of curved jets and damaged jets. But what you can do is kind of estimate what a damaged jet might become by fooling around with the, tweaking how much the radial velocity is of the jet particles and also the tumbling velocity of the jet particles. So you can, but you have to be really careful about how you set those parameters. And but at the same time, it's kind of at the analyst's discretion in understanding how you set the parameters based on what you understand of the situation. So you can, but I would say with caution. I hope that answers it.
All right. And so, hey, Joel, if you or others have a follow-up to that, feel free to throw that in here. I'll move on to Joel's next question, which is, what is the limiting standoff that you have run or have confidence in the results for? 5 meters away from RHA, 10 meters away, you have a known limiting standoff.
For RHA, I think there's really none, because you're either, we start from built-in standoff essentially. So we have an understanding of built-in standoff, and then we can run it all the way out until where the probability of penetration is to 0. That some threats you will have to get very, very far out to get it down to 0, obviously. But as far as kind of running it, there's no limits to it. Whether now there's also this question of, well, are you confident in what it's doing in those high standoffs? We're very confident the closer we get in, because we can look at data to kind of do some sanity checks and scientific checks with the shorter standoff, because there's data out there and we can always do a cross check. But there's not a whole lot of data with much greater standoff. So you can run it, but then the confidence level, if you can't get a hold of test results to check against, starts to drop off. So that's kind of how I would look at it if I was trying to stay out, if I was getting out there further and further. But for shorter distances, for what we understand, we've got, for 5 to 10, for the smaller threats, I think we've got a good handle on that.
Okay.
Over.
All right. From Morton Jensen, are the numerical results verified by experiments? What's the theory behind modeling of the jet breakup?
Well, for RHA, we've done the sanity check with some data that we have gotten from ARL/SLAD. So they had a really nice paper where they characterized penetration at standoff. And we had a chance to look at that, and we had a chance to kind of cross-check it with what we were seeing in SC3D. So there is a cross-check there. Now the theory behind the modeling, and if you're asking, I guess, by the way, Morton, I know Morton, he's cool. Thanks for asking the question. Now, the modeling of the jet breakup is, I guess we can kind of address the theory portion in a couple of pieces. One is that we do have kind of an understanding that yes, the jet does break up, because we've seen it in experiments. So that's the one piece. And then we do have, we like, that's the reference paper that we had looked up, we've gotten from ARL/SLAD, and so it does. But kind of what goes into that is still, I think it's still kind of needed. Some research needs to be done in that area, to what causes it, what's the probability that it'll break up one way or and it's kind of the degree of breakup. So that requires a lot more testing to try to understand. So I guess that's one piece of that question. The other piece is that we're assuming certain things do happen, and it's the thing that we can model, is that these particles, and again, they're based on kind of some background research, that the particles, the jet particle, the straight jet does break up because that shape charge isn't perfect, and especially not perfect when a countermeasure interrupt does something to it to make it imperfect. And so that jet breaks up, and so we make this assumption that the particles break up, and then the little particles will have some sort of radial velocity, and then each one of these particles are indeed um, tumbling as they go through. But at the same time, that I think that piece of it needs to kind of, you really have to really back up and have a good understanding of what's happening in the real world to kind of have a good feel for that. So I hope that answers your question, Martin.
Okay. All right. Um, from Wayne Mindel, with regard to the question about damaged shape charge threat, what would you need from an FEM or particle-based solver analysis of a full shaped charge simulation to add that information to SC3D?
That's the thing. It's tough to do it. I mean, it can be done because obviously you can do like an FEM and pretend a certain damage would occur. Um, and certainly a lot of runs could be used to try to understand that. And I'm not aware of kind of a body of FE type runs or deterministic type runs that have occurred out there, um, where we can go to them. So as far as I know, it's not available. Um, but at the
Okay.
same time, um, anything can happen when you intercept when you have a countermeasure intercept with a shape charge. So we're talking about a variety of damage modes to the shape charge. And once that happens, anything can happen to whatever that shape charge is doing. So you would have to have a bunch of runs with different scenarios to kind of get that understanding. And then once you make those runs, I would assume you would have to do some V&V with testing to prove them out. And so so there's a lot of work to be done, but certainly once we have that understanding, then we could integrate that to SC3D. Over.
Okay. All right, John Otten has got a question for you. He's compared SC3D results to both RPG and ATGM tests, various standoffs, and there's good agreement with the max penetration predictions and test results. Where would you say there are differences with the number of predicted particles and the individual penetration of each particle?
Oh, okay. Boy, you've kind of gotten into John. John. Okay, so John works with Pat Buckley, I believe, and so yeah, so that's I think something that maybe John, Pat, and I could kind of talk
Okay.
more
Yeah.
about.
Well,
So yes, I agree with the final sentence.
sure. Yeah. Finally, discuss that
Yeah,
offline. Maybe tweak that to
yeah,
fit a
yeah.
bit better. Okay. Um, okay. Great. So let me.
That thing
I've got a
that's a follow-on comment to something else.
Yeah, yeah, good. Okay, so then I've got a couple other questions that were still in the chat window. Joel Williamson followed up with, instead of probability of penetration, can you give a predicted variance in RHA penetration over the 50 Monte Carlo runs?
We certainly could include that. I mean, there's nothing that says that we couldn't. I would have to talk to Pat about that, to Pat Buckley. You
Okay.
ask him anything, he'll do it.
Yeah. All right. Um, that may be the last question we've gotten. Um, so I've been told that the slides are now available online, and believe that the link provided a moment ago should be accurate. If again, for any reason, um, it's not, please let us know and we'll push out the updated link. I believe that's now correct. I'll give it another 7 seconds for any additional questions to pop up in the window while I say that thank you to Alex. Alex, great presentation. Really appreciate this. I hope this spurs a bunch of extra discussion among the community.
Sure thing.
Thanks for conducting the service webinar, and thank you, DSI, for making the SNV community aware of it. And if you've got questions, please don't hesitate to contact Alex. All of you participants, by signing up for the webinar, are now in DSIX list of for distribution. So you would have seen that when you signed up. I hope that you can attend many of their other presentations and webinars. Thanks. Any final comment, Alex?
No, apart from, again, parroting your appreciation to the attendees, to DSIAC, and let's not forget Pat Buckley, and to you, Tim, for hosting and being the MC for this. Appreciate it.
Okay, great. All right, thanks all. Enjoy the rest of your day, and have a happy Thanksgiving.